Hey everybody, my name is Eric Sheridan. I'll go ahead and share my screen here. So today's talk is about supply chain security. And the title I gave it was Securing the Supply Chain is Hard, but Don't Give Up. We got to have a positive spin on this. This is a challenging problem and it's multifaceted, affecting many particular areas. What's nice about that from a presentation perspective, that means I could take a topic and position it in different areas for a different audience. And so since we're talking about platform engineering today, I'm going to try and tailor this presentation more toward a platform engineering audience. And so what that means from my perspective is a little bit more of a deeper dive into some of the technologies, a little bit more of a deeper dive into some of the tools, and maybe some examples that can help on your journey to securing the supply chain. Throughout this presentation, feel free to reach out to me. You can always contact me over email, eric@infraredsecurity.com, or you can connect with me on LinkedIn. Or as Maria said, you can always hit me up on the Platform Engineering Slack channel. Cool. All right. So a little bit about myself. So I am a co-founder and managing member over here at Infrared Security. I've actually been working in the application security space for over 18 years now. I have experience doing a number of things: code reviews, pen tests. I've been doing product developments in the security space for a number of years. So I am someone who has a strong both security background and a software engineering background, because I take my knowledge in security and apply it by building products. So that puts me in a position to be able to speak through experience on a number of things that I talk about. And so what's interesting about that is sometimes my experience leads to some outcomes and takeaways from me that work really well. And sometimes I have takeaways that are very different than the experiences other people have. And it's an opportunity for me to learn maybe some of the responses you took to similar challenges. So as I talk about my experiences throughout this, if you had a different experience, if you had a different solution, please share it in the comments. I'd love to hear it. I do look forward to reading those. And feel free to send questions throughout the chat. We'll queue those up for the end. Just a little bit about Infrared Security. So we're a company focused on and specializing in scalable application security awareness training. So we teach folks like developers, architects, testers, managers, the entire product team on all the things necessary to build more secure software, and supply chain security is a big part of that. A little bit about me: I'm a husband and father of 2 kids. I enjoy playing guitar, as you can tell. I also enjoy playing chess, even though I'm absolutely horrible at it. But nonetheless, I guess I like taking a beating. So that's a little bit about me. Let's dive into the topic itself. I want to start this off by trying to define exactly, what is the software supply chain? Because, it's kind of this all-encompassing thing. And really, it is. Yeah, my definition of it over the years now has been that it encompasses all of the people, processes, and technologies used to write, build, deploy, and consume software. So that's the software supply chain. All the people, all the processes, all the technologies used to write, build, deploy, and consume software. So that's a lot. It's a lot, but I mean, it's the reality of the situation that we're in here, that the software supply chain is a lot of moving parts. When I look at the software supply chain through the lens of security, I kind of like breaking it up based on sort of the logical flow and logical sequence of steps software takes from the moment it's an idea in someone's head or on that proverbial napkin someone writes down, to the moment it's out in production, people are consuming and hopefully getting paid well. And I break it up across a few stages here that I will hit on throughout this presentation. Within each one of these stages, I will pause. I will talk a little about some of the risks that you may face from a supply chain perspective, that I've seen customers face from a supply chain perspective, and then talk about some of the things that you can do to improve the overall security posture of that specific phase in the software and the supply chain that's used to create it. So to that end, we'll actually start all the way on the left-hand side, right? So the moment someone has an idea and they do go through the planning phase, we're going to start writing the software to meet, whatever the capabilities are that we all agree to. Right off the bat, this is a great place to start when thinking about supply chain security. Because remember, we talked about it being people, processes, and technologies. So we're starting out with people, right? The first thing we want to think about is like, who is it that's actually contributing to the software? How do we properly verify their identity? And do we trust them, right? You've probably heard about zero trust in this notion that we live in a world now where there's absolutely zero trust. Rather, we verify everything. And so this applies to the people that contribute to the software as well. What is the risk there? Well, the risk there is a good bit, actually. One of it is, having a malicious insider deciding to try and introduce malicious software, or perhaps somebody who contributes to the software had an account takeover, an account compromise. What might happen if a malicious party had access to and had the ability to begin writing software as a means of them potentially contributing to it, or impersonating the identity of someone else who writes your software? There's been some good examples of this trend of focusing on the development team, the people who write software, from a security perspective over the last few years. You can see it in things like, if you look at GitHub's policy in terms of use, in terms of service, and all that good stuff. They actually have a specific section in there speaking to impersonation, right? And that the criteria that if any one of these are met, you are banned from the platform. Because impersonating another developer, can be used to effectively social engineer access to that repo. From a security research perspective, as well as from a hacker perspective, using hacker in sort of the malicious sense, the bad guy sense, there has been a significant focus on developers getting access to their machines, their identities, and all these various services. There was actually a number of state-sponsored attacks that happened over the past few years, where you had these outside organizations, these malicious organizations, contact developers within an organization and say, look, I'm going to give you, if you give me your VPN credentials, I'm going to give you $10,000. You can then just walk away and not worry about a thing, right? Just pretend it never happened. So $10,000 for your VPN credentials, which maybe you need to access some of your privileged development services. If you're someone who is in need of cash, or you're disgruntled, that $10,000 looks pretty enticing, right? And that's a lot of money, period. That's actually what happened to a number of development teams across many significant major organizations, including Microsoft, where you had these criminal gangs, let's say in states outside of the state that the companies resided in, bribing the developers for access, and effectively were able to log in through the VPN as that developer and begin accessing other services, and then do things like putting backdoors in software. You've also have research being done against the open source community itself. So the first bullet I have up there is something about a research paper focusing on this concept of hypocrite commits. And the idea was like the University of Minnesota and a few of the professors and so forth there applied some research to effectively see, okay, Linux, this open source kernel that's used seemingly everywhere, if we could introduce malicious software into Linux itself, pretending to be good developers, can we get it into the mainline code? And so what they did is they intentionally introduced vulnerabilities into the patches that they issued. And so the patches appeared to fix legitimate bugs or issues or introduce new features, but contained subtle security vulnerabilities that, once it was accepted, would put every user and every device that runs Linux at risk. And so what was interesting is that their patches raised a few eyebrows in the community, but effectively they weren't stopped. The patches were accepted. And then at some point, they got called out. There's a combination of them being called out as well as them stepping forward to say, hey, look, we did this research. It kind of happened in parallel. And the Linux community was absolutely furious. They're absolutely furious that these malicious commits were being made because it subverted the integrity of the software they're writing. And the result was like the Linux community completely banned the University of Minnesota from ever introducing software and pull requests associated with the Linux kernel. So that's a pretty significant example of how trust placed in the developers was effectively used against whoever was, believing in the trust of the developers. In this case, it was, the maintainers of the Linux kernel itself. That same concept can happen with our internal projects as well, our proprietary software that is written. So it's a good question of like, how do we trust the developers that are working on our software? There's a few things that help in these sort of situations. The first one is having strong identity management controls. So making sure that there's multi-factor authentication for everything, that the factors used to authenticate are in line with NIST current recommended guidelines. Have it as stringent as possible. And I'm jumping ahead just a little bit here, but things like peer reviews and so forth can help in these scenarios. So that's the first piece of the software supply chain that we need to think about is the people that are writing the software. Now, once those persons have written the software, at some point, they're going to want to make a commit and share that software with other teammates. That's where we start having source code being contributed to source code repositories. So we get into like the share phase here. And this is where you want to think of things like authentication and access control. Who has access to the source code repository? Who's allowed to make commits to that repository? How is that repository configured from a peer review process? A number of organizations I have worked with have this sort of public read-only access to all their code. So even if if it's proprietary software within the organization, anybody who's within the corporate network can see all of the code throughout the organization. The intent behind it was well-meaning, trying to encourage collaboration, but a lot of the times the source code repositories themselves contain secrets like passwords and so forth that were disclosed to unauthorized actors. So like understanding what goes in that source code repository is very important, making sure that we lock down this system as well. Things like, once again, multi-factor authentication, having peer reviews set up within GitHub are all important to restrict access to the source code repository. So things I talked about thus far do not get a lot of attention from a supply chain perspective, even though they're very important. The next one really gets a ton of focus, and that is the build phase, right? So the moment that our build pipelines pull down the source code from wherever the repository may be housing it, it's then going to go out into the internet, internally or externally throughout the internet, and pull down various artifacts needed to build the software. So it's going to be connecting to things like, Nexus repos or npm.js and all these other places where third-party dependencies and frameworks lie. It's also going to be accessing other external services. It may access identity services, database services, and other things that might have information and artifacts needed to be pulled together to make the unit of software that's about to be distributed. This area gets a lot of attention. Because there's a lot of moving parts, there's a number of things that could go wrong. One of the key issues is like having hard-coded secrets within this environment, right? So hard-coded keys and passwords that are accessible within the source code that are visible in plain text if you access whatever it is, the console or interface to that build system or server that you happen to use. Once that's disclosed, right, the attacker can use it at free will. Another thing to keep in mind is the build environment hardened? Have we applied the things that we've learned over the past many decades that we seem to apply by default, at least I hope so, in production environments? Are we applying that in the build phase as well? Are our build servers, build environments, the networking below it and above it and all around it, has that been hardened and secure? Very rarely do we look at the build environment with the same lens as the production environment from a security perspective. And as a result, there seems to be a lot of vulnerabilities and misconfigurations in this world. You also have the consumption of third-party components. And the thing you need to be mindful of is the moment you actually pull in a third-party component to your software, you assume it's risk. So if it has vulnerabilities or it has a license that sort of conflicts with the intent of the software you're creating, you've introduced a significant amount of risk, potentially vulnerabilities within your software as a result of the supply chain. This time, instead of people, it's all about the technologies that you're pulling in. So this gets discussed a lot because of the many big issues that have come up over the years. There's a few key ones right off the bat we'll highlight. The first one is the log4shell debacle. I think it was late 2011, or not 2021, where there were vulnerabilities discovered and disclosed in log4shell, where any Java application that uses this library, log4j, which is like almost every Java library or Java application out there uses this library. If it used this library and logged a user-supplied input, that user-supplied input could have a payload that, I kid you not, got the log4j library to connect to a remote LDAP server, pull down a class file, which if you don't use Java, that's compiled code, and run it within the context of that application. I don't know. I'm not privy to the design decisions and feature requests that went into building this capability within a logging library, but I would have never guessed that a logging library would have that sort of thing built in. And so I've got kids who play Minecraft. There's a heavy community around Minecraft that's focused on the Java edition. I actually had to go in and make sure that their systems were patched, because all they had to do was log into a Java server, and anybody else who's also in that server, if they send a Minecraft chat message with the payload in it, everybody on the server, including the server itself that is not patched, is immediately exploited. Right, so it's pretty massive. You then had SolarWinds. Right, so SolarWinds happened, I think, about a year prior in 2020. And so this was where an insecure build environment was exploited, such that attacker was able to introduce malware into the final build product. Now, what's interesting is the attackers did not modify the source code. What they did is they actually were able to obtain a privileged service account remotely and log into one of their build servers, and saw that their build servers pulled artifacts from different locations, one of which the attacking organization found out they could control. And so they were actually able to introduce malicious code that patched the software and products being produced by SolarWinds without touching the actual SolarWinds code itself. And so this was used throughout the world, including all these government agencies. And it left a significant amount of those organizations and industries vulnerable to attack as a result. You also have a number of third-party libraries becoming more malicious, as well as you have more, like, I'll call it protestware, which is an open source developers taking some initiative, taking some stance from a protest perspective, and using the open source software that they write or maintain as a means of communicating that message. So you have things like type squatting, which has been around for a while. But then you have, like, a few examples here. Like, there was this library called Colors and Faker, both by the same maintainer. And these were libraries that are effectively downloaded millions of times a week, I think over 8 million times. And so anytime you would run an application that uses dependency, your application would print like this garbage out onto your screen and basically have your application sit in an infinite loop. And so these dependencies impacted a lot of projects, including AWS's SDK. Anybody who used AWS SDK, when it was dependent on these vulnerable versions, their applications just sat in an infinite loop. So it's pretty disruptive. Then you have a library called Peace Not War, which is actually made as a dependency of a more popular library. Anytime your application ran with that dependency, it would print out these messages on your console and also create a file on your desktop, effectively providing an opinion or stance as relates to the conflict in Ukraine. So these are things that are very disruptive from a software delivery perspective. As a result, one of the key things that has really captured mind share over the past few years is something referred to as a software bill of materials. The Executive Order 14028 in May of 2021, entitled Improving the Nation's Cybersecurity, was this memo that demanded and required federal agencies and organizations who do work with federal agencies to adhere to some standards by some period of time. And it was very much focused, a good bit of it was focused on supply chain security. And so while the term software bill of materials was not necessarily invented with this memo, it became a very commonplace term as a result. So software bill of materials is very much like the nutrition ingredients and the nutrition label on food, right? So like when you go shopping for food at the grocery store and you decide whether or not you want to buy that particular item, hopefully you're looking at the back, looking at the ingredients that go into it and deciding whether or not it is or is not safe to put this in your body. Same thing with software. The software bill of materials describes all the things that went into creating the software, the components, the dependencies, the compiler tool chain, the third-party services, all of this stuff, so that people who go to consume your software will have this information available so they can make a determination somehow as to whether or not they are actually going to use your software. So an SBOM is this concept. There are like 2 to 3 major specifications that are widely adopted. One is called Cyclone DX, which is the one I'm more familiar with, but there's a couple others as well. At the end of the day, you just kind of need to pick one that works best for you, your technology stack and your tooling. But it's a nice standard and way to capture this sort of information, the stuff that goes into assembling and creating our software. So once we get out of the build phase and we start to create some artifact, as a part of that, we are testing that artifact. Now, depending on the organization, this testing may actually happen within the build pipeline itself, or it may be viewed as a separate phase of your development process where you actually have some manual testing or a QA team focused on testing that software. Here's where I want you to start thinking about things like tools and the attestation of the software that you're creating. There are a number of emerging open source tools and technologies in this space that, from a platform engineering perspective, I think it's good to just be mindful of if you aren't already, and hopefully you consider adopting as a part of your overall tool chain and solutions. The first one I want to call out is SIFT. So SIFT is pretty cool in that it's this open source project that has the ability to scan your container images or scan your file system and recursively look for indications of something representative of software and the software that it depends on. And it'll pull all this information together and create an SBOM for you. I like it because you can take SIFT, point it to a directory, just say go, and it gives you all this information, which is pretty cool. The other thing that it can do, which I like, is that it can actually sign SBOMs. So digitally sign SBOM attestations using a specification called in toto. In toto specification is actually recommended by something called the SALSA framework, which I'll mention a little bit later. But at the end of the day, it's a really nice tool to start generating SBOMs. And so if you don't have a solution already today, and you want to start somewhere without incurring hard, real budgetary dollars, SIFT is a great place to start. The other tool I'll call out is very complementary. It's called Gripe. So Gripe actually has the ability to scan the same things, container images and file systems, to identify those third-party components that go into your software, but then tell you whether or not it believes that there's an associated CVE or known exploitable vulnerability associated with that component. And if so, it'll surface that information to you. What I like about this is Gripe has the ability to also ingest SBOMs generated by SIFT. And so, with a few lines of code in your build pipelines, you can actually generate SBOMs, test them for vulnerabilities, and optionally fail the build or fail the pull request. based on some policy that you decide to stick to. So if you're not using them already, these are great open source tools to check out, but they are by far not the only ones. Software supply chain security is very much an emerging trend. There's a lot of hype around it. And so there's a lot of interest and competing tooling that's being created, which is good because at the end of the day, that means we have a lot of opportunity for great tools to come out of it. Another one I will highlight is based on my personal experience, and it's called License Finder. So I build software and I work on the build systems and build infrastructure that helps automate the packaging release of that software. So one of my responsibilities includes making sure that whatever components we use, their licenses is friendly to the software that we're building. So if we're building proprietary software, things like the GPL or AGPL may be problematic depending on the context. What I like about License Finder is, once again, you can point it to a directory and recursively scan it and find the licenses, and then it'll give you the ability to enforce policy. So we actually have a policy that says, for certain projects, these are the licenses that are allowed, and these are the specific components that are allowed. Anything else is rejected. So if we have a developer on a team introduce a third-party component that does not meet that policy, our build fails, the pull request is rejected, and it sparks a good conversation. The reason I'm calling out License Finder is because not only do we need to worry about vulnerabilities, but we also need to worry about the licensing risks from a legal perspective with the software that we use. But that my experience when using SIFT was a bit mixed when it came to its ability to determine the licensing information with third-party components. So SIFT did a great job at identifying third-party components, but the licensing insights that it gave me was, in my experience, was a little bit less than what I got out of License Finder. And so as a result, right now I'm using a combination of them. So let's take a look at an Azure Pipelines job definition so you can get a sense of kind of what it looks like in our systems. And once again, this is a great opportunity to look at the stuff I have here and say, Eric, there's a way better way to do it. And if so, please let me know in the comments. So if you haven't used Azure Pipelines before, it's yet another YAML file. And in here, you define a number of jobs. And I have a job here called policies. And so it's a Linux-based build. And you can see the steps here probably have about 7 or 8 steps, or rather 5 steps. The first couple steps are just kind of setting up my environment. Like there's installing NuGet, which is needed by License Finder. Doing some configuration with my environment variables to ensure like my Ruby gems and so forth are picked up. I go ahead and actually install things like some Ruby gems, but I also install License Finder. And then if you can see my mouse pointer, then we get to this license verification section. There are some interesting things here in my experience using License Finder. You see this first line in here, it says bundle install gem file, and then the name of the gem file itself. If you're not familiar with Ruby applications, gem files and the program bundle are kind of how you both declare dependencies and then install them respectively. So I actually had to install, run this command on one of my gem files for License Finder to give me some more information. I had to do that with Ruby. I don't think I had to do it with the other projects. And I had like a Java project, a Rust project, a Go project, Python project in there. So anyway, it's worth calling out. We then have this command here that says License Finder report recursive format CSV. And so what this line does is basically says from this directory onward, recursively, look at all the dependencies that we find, extract all the licenses, save it in a CSV file, and I actually save it to my artifact staging directory so that when this build finishes, one of the artifacts attached to that build are all the licenses used. Are all the licenses used with that. We then go down to the third line here, which says License Finder action items recursive. This will actually enforce my policy. So if any one of those licenses does not meet our policy, it has a negative non-zero exit code and the build fails. Assuming that all license verification passes, then we go through and do some SBOM generation. So you can see here's the 2 lines of code that I use to actually run SIFT. I run this curl command with an install script that actually installs SIFT locally within this virtual machine or container, whatever's under the hood. And then I call SIFT on the current directory and just save the file in the cyclone.dx format in the staging directory. So once again, it's another artifact that's attached to my build. Similarly, once that's finished, I install Gripe another one line command, and then run gripe using the SBOM file as input. And then I save the output as this additional JSON file, which is enriched. Since we're going to share those slides, I will fix that typo. Cool. And then once all that's finished, we then publish the artifacts, and we have a condition of always. So regardless of whether or not the build passes or fails, whatever artifacts generated, we want to save them. So what's cool about that is from a supply chain security perspective and from an open source perspective, there's a few things you could do right there within your build pipelines that cost $0, but add a good bit of value. Once we get past the test phase, we start getting into deployment. Once we package our software, we then want to make it available to our users for consumption. So we're going from this phase, from the build phase to the deployment phase. Whatever was built over here, we need to make sure that whatever that is the same thing that gets deployed. In the SolarWinds example, this was problematic because the thing that they built and intended to build was different than the thing that they actually deployed because of the whole process and how that worked. So that's where we get into things like, hard environments, and the repos and so forth that are used to contain our software. And then we also get into integrity issues like, what confidence do we have that what's being deployed is the same thing that was built? Now, what's interesting is we kind of live in like a container world, if you will, where containers are used as almost the de facto package for software these days, at least in sort of a SaaS world or a distributed computing world or microservices world. What's cool about that is that there's a technology released called cosign. And what cosign gives you the ability to do is actually sign your container images. So in step one here, I actually go about generating a key pair. In steps two shows an example of how I go about signing the image itself. And then step three shows how I go about verifying the image. So what's cool about this is a part of my build pipeline, I actually sign my image before I push that image to a repository. And the repository can be configured, depending on what version you're using, to make sure that whatever is given to it, the repository, is digitally signed by an authorized signer before it is accepted. If you're using a GCP, there's a technology called binary authorization. And so this is like a container registry capability that allows you to enforce the requirement that all images and containers, or images rather, that are pushed to this registry be digitally signed. If that criteria is not met, the image and push is rejected. It also gives you the ability to enforce things like security vulnerability and security posture of the image as well. So like if the image has a critical vulnerability on it, you can configure binary authorization to actually reject that image. The next piece is once the software is deployed, how do our consumers verify the authenticity and integrity of the software? Right? If you go look at a lot of supply chain write-ups, maturity models, they will encapsulate the concept from write all the way to deploy that I have here. But I really do not see, commonly at least, people talking about this last step here, the consumption. But this is a pretty big and important part. Right, so if you're someone who consumes software, you really want to have the ability to make sure that the thing that you download and the thing that you consume and are about to run is what the author intended to give you, which means you need to have the ability to verify the authenticity of the author itself and the integrity of the artifact that was given to you, which at the end of the day, once again, requires the use of digital signatures and cryptography for things like identity management. This actually has resulted in a number of issues over the years. You have things like WordPress installations where there's a lot of fake or malicious updates that are going on. So people who have WordPress instances, they go to update it, and they get these updates that are not from the author that they thought they were pulling it from, and end up installing malware in the WordPress instance, and the thing gets owned. You have smart cars that are getting hacked fairly frequently these days. And when they do, they get a lot of attention because you take cybersecurity and you now make it relatable in the real world, right? There's physical damage that can happen to us and ourselves and our bodies when a car is hacked. And so you had an example here of like how Honda Civic cars were hacked such that a hacker could remotely unlock the car, remotely start the car, right? And so that raised a whole lot of eyebrows and issues. And the problem stemmed from the fact that the device, when you buy the car, you get like a device to remotely control it. That device and that car were communicating these messages, but the car did not have the ability to properly verify the authenticity of the key holder, right? The messages and so forth were common, and as a result, they could be spoofed and replayed. And so as a result, the car would happily accept the instructions and what is being told from whoever happened to know that code, and that's what the hackers are able to exploit. Another good example of this actually impacted Comcast a few years back, where researchers were able to have malicious firmware installed onto a TV remote and effectively could turn it into a listening device. The way they did this was kind of interesting. So the TV remote would constantly send out this signal, like a radio signal, saying, hey, does anybody have an update for me? Anybody have an update for me? And the Comcast receiver device would periodically say, yeah, I've got something for you. Here you go. Yeah, go install it. And so the Comcast receiver is actually connected back to headquarters, right? So it's pulling the upload, the firmware from a trusted location. But it then just passes to the remote when it hears the remote say, hey, does anybody have any updates? What the researchers were able to do was intercept the communications between the remote and the Comcast device by effectively performing a denial of service attack remotely against the receiver, and spoof the messages of the receiver so that when the remote said, hey, does anybody have any updates for me? They were able to pretend to be the receiver and say, hey, yeah, I have some updates for you. Here you go. And the phone would just take whatever was given and install it and run it. So the remote, which in this case is the user, had no meaningful way to properly verify the authenticity of whoever created the software that it was given. It could not verify that the software was given was actually created by Comcast. Now, going back to the container world, and particularly in this case, the Kubernetes world, there's a number of technologies out there that can help if you're deploying in Kubernetes clusters and so forth. We talked about Cosign, which is an open source technology that can be used to digitally generate keys and digitally sign images. But if you're operating Kubernetes clusters, there's an open source project out there called Connoisseur. Apologies, I know I botched that. Which actually has the ability to be installed as an admission controller. And so what this means is like anytime there's an image that's coming in or a pod that's about to be booting up within the cluster, it goes to this admission controller, which can basically do whatever it wants, right, to determine whether or not the admission is authorized. And so what Connoisseur does is it'll say, okay, is the image that this pod is about to pull from the startup, is this digitally signed? And if not, we're going to reject the attempt. And so the attempt to start the pod will fail. If the image is digitally signed, it will then go through and verify the digital signature, make sure it's valid. If the digital signature is not valid, it'll reject the pod will fail. If the signature is valid, then it will allow it through. So what's cool about this is actually by running like a few lines of command line code, including running helm install, you can actually get this thing installed in your Kubernetes cluster as a mission controller, and it will automatically enforce the requirement that all your images be digitally signed by a certain authorized party or parties before they can be deployed to the cluster. So in this case, the user is your Kubernetes environment. And with Connoisseur, you're giving them the ability to verify authenticity of the author. So when you pull all this together and look at the supply chain from a security lens, there's a ton of moving parts in here. And so from a platform engineering perspective, there's a number of parts in this that you can influence, whether it be the systems that are used to house the source code, or the build infrastructure that you create and automate, or the deployment infrastructure that you manage and automate, or if you're operating Kubernetes clusters that consume the results of a supply chain or consume software, there's things you can do there to make sure you can verify the authenticity and integrity of that software as well. That's why the software supply chain and the security of it is a rather complex topic, just because there are so many moving parts. What's cool is, since this is an emerging area, you have maturity models popping up that you can use to help jumpstart your efforts. The SALSA, which stands for the Supply Chain Levels for Software Artifacts, is one that has gotten a lot of attention recently, largely because it advocates for open source tooling, it offers open source tooling, and it's backed by major entities, including CNCF, Google, VMware, Datadog, and that's actually led by the Linux Foundation. So if you're looking to jumpstart your software supply chain efforts and be able to somehow measure yourself so you can set sort of a roadmap for improvement, check this out. This maturity model is pretty easy to digest and a great place to start. I'll just kind of briefly summarize here. What are the next steps? If you're on the product development team, you're going to have to verify the authenticity and integrity of everything and be prepared to prove it. If you work with or are part of the sales and customer facing teams, you're probably going to start getting questions from your customers if you haven't already, or what is it that you're doing from a supply chain perspective? So have your responses ready. From an executive leadership perspective, you're going to need a game plan and associated resources to reduce whatever the risk of the supply chain to an acceptable level, which implies you know what your risk is today and you know what acceptable level is for you. For everybody else, it's a mindfulness exercise, right? Supply chain security is very complex. You want to ask yourself, how can I help? What is it that I can do within my organization? For us, since we are an education company, what we can do is actually create educational materials to help organizations accelerate the supply chain security efforts. So we actually have a course on the supply chain security as well. So with that said, that'll conclude my presentation. I think I went right up to the minutes, but I can stick around for a few more minutes to do some Q&A. Otherwise, thank you all for your time.
Thank you so much, Eric. It was very insightful with lots of interesting stories and cool tools to use. And you can see in the chat that many people are very excited. But we got some questions in the chat going on. But guys, feel free to put in more questions. Please put them in the Q&A section so we can see them better. But if you put them in the chat, that's also cool. So most vulnerability scanning tooling needs quite a lot of configuration, which vulnerabilities to scan, etc. How is that for RIPE?
Yeah, great question. So if you're dealing with vulnerabilities in the software that you write, there's a lot of configuration often that needs to be done based on the tooling. What I like about GRIPE is it's targeting a problem that's fairly consistent across environments, and that you're looking at known software artifacts. So really it's just a question of, can GRIPE properly identify the components that are being used, and what is your policy? What is your tolerance or threshold for the vulnerabilities that it identifies? And so from a configuration and policy perspective, it's really about, each vulnerability has a severity. What is your cutoff point? Right? If there's a severity greater than, I don't know, medium or high, maybe that's when you decide to fail the build. Outside of that, I've not had to really do much configuration with GRIPE beyond that, which is pretty cool and actually fairly rare, as your question kind of implies with security tooling.
I don't know if that's a question, but more of the comment. Feel free just like to comment it. So Avast Top CI/CD Sec2 and Sec2 also specifically addresses supply chain attacks and pipeline-based access controls. which is very good development for securing software supply chains.
Yes, thank you for mentioning that. So since it's an emerging industry, we have a lot of like standards coming out in taxonomies. And I think the OWASP top 10 for CI/CD actually came out as well. So there are a number of good resources at OWASP that you can look to when you're looking to improve your supply chain. So thank you for calling that out.
And another thing, which is more of the comment as well, I guess another issue at the right stage is that many developers and administrators will load various kinds of software without inspection or recording the use to management security. Examples include editor, different plugins, utility scripts.
Yeah, that's pretty common, and that's a bit of a weakness in some of the supply chain tooling that I've seen. There is quite a bit of a focus on the build stage, but I don't see a lot out there for like, what is the software that's running on our laptops, like IDEs and plugins and so forth to do this. It turns out to be a manual exercise. I don't have a good automated solution for that. So if you have an experience where you're able to sort of streamline that, I'd love to hear it.
Yeah, I don't see any questions coming in, but if you have, please either throw them in the chat right now, or you know where to find Eric. He already has provided the email and platform engineering Slack. I posted the recording from this webinar, but thank you very much, Eric. I was very looking forward to the end of the presentation where you play your guitar, but next time we'll invite you for a solo concert.
I'm actually pretty shy, but maybe another time. Okay.
Yeah. We got your word. And yeah, thank you everyone who joined us today. We have webinars, platform engineering webinars every week, so you guys can check it out and sign up to the interesting one. And of course, I'm sure that you're a part of the platform engineering Slack already. So thank you for joining, and we'll send over the slides and recording tomorrow. Have a great day.
Thank you.
Bye.